There's a photograph sitting inside NASA's servers right now that most of humanity does not fully understand. Not because it is complicated, because nobody's telling you what it actually means. Scientists looked at this image and went silent. Not the kind of silence that follows confusion, the kind that follows the moment when everything you thought you knew shifts 1 inch to the left and suddenly the entire landscape looks different. A machine floating 1,000,000 miles above your head just stared into the darkness of space and found something that was never supposed to be this easy to find. Another world. A real one. And now nothing in astronomy will ever be the same again. For 30 years, the search for planets beyond our solar system was essentially a guessing game dressed up in mathematics. Astronomers were not really seeing other planets. They were inferring them. They were watching a distant star and waiting for it to blink, that almost imperceptible dimming of starlight that happens when a planet passes between the star and the telescope. A shadow, a flicker, a statistical argument, wrapped in observation. That was the best we could do for decades. And it worked remarkably well, in the way that reading a person's footprints in sand works. When you want to understand who walked by, you can learn things, but you are never actually seeing the person. You are seeing evidence that they existed. That distinction matters more than most people realize, because here's the truth that the scientific community has been sitting with quietly for a generation. Nearly every single one of the approximately 5,900 confirmed exoplanets ever discovered was found, without us actually seeing it. Let that number settle. Nearly 6,000 worlds identified in the cosmos, and the overwhelming majority of them were invisible to us in any direct sense. We knew they were there, the same way you might know there's a ship on the ocean at night, because you can see the waves it leaves behind. The ship itself remains hidden in the dark. The James Webb Space Telescope, a machine that cost $10 billion and took 3 decades to build, turned its eye toward a young star called TWA-7, located approximately 111 light years from Earth in the southern constellation Antlia. What it captured in that image was not a shadow, not an inference, not a mathematical probability dressed in the language of confirmation. It was an actual planet, a faint, warm infrared glow sitting inside a ring of cosmic debris, unmistakably there, undeniably real. The first exoplanet that James Webb had ever directly discovered through its own imaging. Scientists called it TWA-7b. And when the research was published in the journal Nature, the response from the astronomical community was not celebration first. It was disbelief, then silence, then the slow dawning understanding of what this single orange dot in a photograph truly represented. To understand why this image broke something open in the world of astronomy, you have to first understand the fundamental problem that has haunted planet hunters for as long as direct imaging has existed. Imagine trying to see a firefly hovering directly next to a lighthouse beam, not somewhere near it, right next to it. The firefly produces its own light. It is real. It is there. But the lighthouse is so overwhelmingly, catastrophically brighter that the firefly simply vanishes in the comparison. Your eyes, no matter how well trained, no matter how powerful, cannot separate the two. This is what astronomers face every time they attempt to photograph a planet around a distant star. The star is not just brighter. It is billions of times brighter. The planet is the firefly. And the star is not a lighthouse. It is a nuclear explosion sustained across millions of years. This is the wall that astronomy has been running into since the very idea of direct exoplanet imaging was first proposed. The few planets that had been directly photographed before Webb were enormous. We are talking about gas giants many times more massive than Jupiter. Young planets that were so freshly formed they were still radiating enormous amounts of heat, glowing like dim stars themselves. Those planets could be seen not because they were easy to find, but because they were exceptional. They were outliers, freaks of planetary science. Objects so much hotter and larger than typical planets that they pushed through the noise. Every other planet, the ones more comparable to the sizes and temperatures we actually care about when searching for worlds that could sustain life, remained completely invisible to direct observation. What James Webb brought to this problem was not just more power, it was a different kind of weapon entirely. The critical technology that made the TWA-7b discovery possible is called a coronagraph. And if you have ever watched a total solar eclipse, you have already seen the natural version of this concept. During a total eclipse, the moon's disk blocks the overwhelming light of the sun, and suddenly the sun's outer atmosphere, the corona, becomes visible, a structure that exists all the time but is completely drowned out by the sun's. Brightness suddenly becomes real, visible, and extraordinary. The coronagraph does exactly this artificially. It creates a controlled, engineered eclipse inside the telescope itself. A mask, precisely shaped and positioned, blocks the light of the host star, suppressing its glare so dramatically that the much fainter objects nearby can finally be detected. The coronagraph, installed inside Webb's mid-infrared instrument called MIRI, was developed by French scientists at the CNRS in collaboration with Durham University in England, and it performed at a level that even its designers described as remarkable. According to scientists on the project, Webb's coronagraph increased the ability to detect exoplanets through direct imaging by a factor of 10 compared to what had been possible before. Think about what that means. Not 10% better, 10 times better. An entire order of magnitude leap in our ability to see what was previously invisible. The team that made this discovery was led by Dr. Anne-Marie Lagrange, an astrophysicist at the French National Center for Scientific Research and the Observatoire de Paris PSL. Her team had been watching TWA7 specifically because this star had something unusual about it. At just 6.4 million years old, TWA7 is extraordinarily young by stellar standards. Our own sun is approximately 4.6 billion years old, which means TWA7 is younger than our solar system by a factor of roughly 700. This star is so young that it is still surrounded by a swirling disk of dust and rocky debris, the raw material of planet formation that has not yet had enough time to fully assemble itself into complete worlds. Ground-based telescopes had already identified 3 distinct ring structures within this debris disk, concentric bands of material separated by gaps. And those gaps were the clue that attracted Lagrange and her team. Because in planetary science, a gap in a debris disk is not simply an absence of material, it is a signature. It is the fingerprint of something that has cleared that region, something massive enough and gravitationally powerful enough to sweep the debris away as it orbits. It is, in other words, the exact kind of evidence you look for when you suspect a planet is hiding in plain sight. The footprints in the sand, the wake of the ship at night. The team decided to point Webb directly at this system, and on June 21st, 2024, the telescope stared into the debris disk surrounding TWA7, its coronagraph blocking the star's light with extraordinary precision. And in the gap between the first and second ring, in exactly the region where a planet should have been based on everything the debris disk structure was suggesting, there was a faint point of infrared light that had no business being there unless something significant was orbiting that star. The object they found, now called TWA7b, sits approximately 52 times farther from its host star than the Earth is from our Sun. To put that in perspective, even the outermost planet in our solar system, Neptune, orbits the Sun at roughly 30 times the Earth-Sun distance. TWA7b is orbiting even farther out than that, a remote world in the cold outer reaches of a young planetary system that is still in the process of being born. Its mass is estimated at approximately 1/3 that of Jupiter, which makes it roughly comparable to Saturn in our own solar system. But here's the detail that fundamentally separates this discovery from everything that came before it in the history of direct exoplanet imaging. This is not a super-Jupiter. This is not a bloated, extraordinarily massive outlier. This is, for the first time ever, the lightest planet that human beings have ever directly photographed outside our solar system, by a significant margin. And that record-breaking number is not just a trophy, it is a door. Every time we have lowered the threshold for what we can directly see, we have found more. Every time a new generation of technology pushed the floor of detectability a little further down, the universe has rewarded us with discoveries that changed our understanding of what is out there. For decades, direct imaging could only show us the giants. Now, Webb has shown us something closer to Saturn's weight class, and the scientific implication of that progression is almost impossible to overstate, because the direction of that trajectory leads, with patient and inevitable logic, toward Earth-sized planets. Read that again, carefully. The direction of that trajectory leads toward Earth-sized planets. We are not there yet. Nobody is claiming that Webb will photograph another Earth tomorrow, but the gap between where we were before this discovery and where we are now represents a generational leap in capability. Before June 2025, direct imaging of exoplanets was a technique that could only reveal monsters. After June 2025, it is a technique that can reveal something approaching the middle class of planetary formation. And the scientific path forward from here bends consistently towards smaller, cooler, more Earth-like objects. Dr. Lagrange herself was explicit about this when discussing the results. She noted that this discovery represents a new step in the research and direct imaging of increasingly small exoplanets, objects that are more similar to Earth than to the gas giants of our solar system. The JWST, she said, has the potential to go even further. But what does further actually look like? And why does it matter as urgently as the scientists are suggesting? Here's the part of this story that most coverage is glossing over entirely. The significance of the TWA7b discovery is not just about what was found, it is about what it confirms regarding a method. For decades, astronomers have been arguing about the best approach to eventually finding and characterizing potentially habitable worlds around other stars. The transit method, watching planets pass in front of their stars, is extraordinarily powerful for finding planets in tight orbits close to their host stars. But it tells you almost nothing about what the planet is actually like unless you can follow up the discovery with spectroscopy of the planet's atmosphere as starlight filters through it. And it fundamentally cannot reach planets in wide orbits, the kind of orbits where a planet might be temperate and potentially interesting for life. Direct imaging, on the other hand, can target those wide orbit worlds. And critically, because you are capturing the planet's own light directly, you have immediate access to its spectral signature. You can analyze the light coming off the planet itself and identify what chemicals are present in its atmosphere. The combination of Webb's direct imaging capability and its extraordinary spectroscopic instruments means that the discovery of TWA7b is not just a photograph. It is a proof of concept for a scientific pipeline that could eventually tell us not just where other planets are, but what they are made of and whether they could sustain the conditions that life requires. That pipeline is now open. It has been tested. It works. And now the scientific community is rapidly identifying the next targets to run through it. According to informed sources within the exoplanet research community, the success of the TWA7 observation has already triggered a broader observational campaign. The CNRS team and their international collaborators are now applying the same coronagraphic approach to other young nearby stars with structured debris disks. The logic is straightforward. If gaps in a debris disk are signatures of hidden planets, and if Webb can now directly image planets down to Saturn's mass class, then every structured debris disk in the stellar neighborhood becomes a target worth examining with extreme care. What most people are not seeing is that this single discovery has essentially transformed a list of candidate systems from theoretical exercises into serious observational priorities. The follow-up campaign is already underway. There's also a second layer of significance buried inside the details of this discovery that has barely been discussed in mainstream coverage. The debris disk surrounding TWA7 is an extraordinarily young structure. At 6.4 million years old, this system is still in the active process of planetary formation. Most of the planets we have studied before, even through indirect methods, orbit stars that are mature in the way our sun is mature. Billions of years old, the planetary architecture fully settled. The violence of early formation long since quieted. TWA7 is the opposite of that. It is a system caught in the act. And TWA7b, sitting inside a gap it carved out of a primordial debris disk, is a planet that we are watching emerge from the chaos of stellar birth in something approaching real time. For the first time, we are not just cataloging distant worlds, we are watching one be made. Think about what that means for our understanding of how planets form. For decades, the models of planetary formation have been built on inference, on theoretical physics, applied to what we could measure indirectly. We understood the dust clouds, we could model the gravitational dynamics, and we could look at mature solar systems like our own and work backward to reconstruct what the formation process probably looked like. But we had almost no direct observation of a planet caught in its own infancy inside its birth disk. TWA7b changes that. It gives theorists a living test case. The gap it has carved, the ring structure it has shaped around itself, the way its gravity has organized the debris disk around it into those three concentric rings, all of that is observable now directly with the most powerful space telescope ever built. The implications for planetary formation theory are profound, and then there's the question of what comes next, and why the answer to that question is making astronomers simultaneously excited and anxious. The extremely large telescope, currently under construction in the Atacama Desert in Chile, is expected to come online around 2028 to 2030. With a primary mirror spanning 39 meters in diameter, which is roughly the size of a large office building, the ELT will dwarf every ground-based telescope that has ever been built. Combined with advanced adaptive optics that can correct for atmospheric distortion in real time, the ELT is expected to achieve direct imaging sensitivity that goes dramatically beyond what even Webb can accomplish from space. Theoretical models suggest that the ELT could potentially directly image planets in the size range of several Earth masses around nearby stars. Not Earth itself, not yet, but something approaching it, something in the neighborhood. And beyond the ELT, there is the Habitable Worlds Observatory, a space telescope concept that NASA has been developing with an explicit stated goal of directly imaging Earth-like planets around Sun-like stars and searching their atmospheres for chemical signatures of biological activity. The kind of signatures that life, and only life as we understand it, would produce. The target date for the Habitable Worlds Observatory is somewhere around 2040. That sounds distant. It is roughly a decade and a half away. But consider that 15 years ago we did not have James Webb. We did not have confirmed atmospheric detections of specific chemicals in exoplanet atmospheres. We did not have a single directly imaged planet lighter than Jupiter's mass class. In 15 years, the field went from theoretical aspiration to TWA-7b. The next 15 years, building on the foundation that this June 2025 discovery just cemented, could go further than most people currently dare to imagine. But there is something important to hold alongside all of this forward momentum, something that the most thoughtful scientists in this field are careful to say out loud. The road from TWA-7b to a directly imaged Earth-like world around a sun-like star is not a straight line. It is an escalating series of technical challenges, each one harder than the last, each one requiring instruments and approaches that do not yet fully exist. The coronagraph technology that made TWA-7b possible is extraordinary, but it is not sufficient for the next step. The contrast ratios required to image a genuinely Earth-sized planet next to a sun-like star are roughly 10 billion to 1. 10 billion. The faint glow of a true Earth analog is so overwhelmed by the light of its star that the engineering required to separate them represents one of the most difficult precision challenges in the history of scientific instrumentation. We are not there. We know the path. We do not yet have all the tools. What most people are not seeing is that the TWA-7b discovery functions as both a triumph and a marker. It is the scientific community planting a flag at the edge of a new frontier and saying, we have crossed this threshold. What lies beyond is real, accessible with more work, and worth every ounce of effort and funding we can bring to bear on it. The discovery simultaneously celebrates how far we have come and makes visible with unusual clarity how much further we need to go. And there is one more dimension to this story that almost nobody is talking about, one that lives not in the telescope specifications or the orbital mechanics, but in the deeper question of why any of this matters to ordinary people who have never looked through a telescope in their lives. When James Webb captures a direct image of another world, a real planet orbiting a real star in the real universe, it is doing something that transcends the technical achievement. It is making the cosmos visible in a way that goes straight past the intellect and into something more fundamental. That faint orange dot in the image is not an abstraction. It is not a number in an equation or a dip in a light curve. It is a place, a world that exists, that has its own structure and mass and gravity, that is sitting inside a disk of ancient stellar material and slowly organizing the universe around itself the way planets do. And we can see it with our instruments, with our ingenuity, with a telescope that we imagined, planned, built, launched, and aligned with almost incomprehensible precision, 1 million miles from Earth, staring into the dark. According to informed sources close to the research team, the initial reaction among the scientists when the processed image was first examined was a quality of quiet that the laboratory is not used to experiencing. The kind of quiet, as one team member reportedly described it, that happens when you realize you are the first humans who have ever seen this particular thing. Not just discovered it, seen it. There is a difference. And that difference is what the TWA-7b photograph represents at its most essential level. The real story is not just that James Webb found a planet. The real story is that humanity has now demonstrated, for the first time, a genuine capability to look at another world in another solar system and say, we see you, not your shadow, not your footprint, not the ghost of your gravity and the motion of your star. We see you directly. And that sentence, once it becomes routine, once it describes not a historic first, but a standard scientific procedure applied to dozens and then hundreds of candidate worlds, changes everything about what it means to ask the question that has driven this entire enterprise from the very beginning. That question has never been closer to having a real investigative methodology behind it. Not faith, not philosophy, not the mathematics of probability applied to an unknowable cosmos. An actual method, a working telescope, a proven technique, a published discovery in Nature, and a future full of instruments more powerful than anything that has yet existed, pointed with growing precision at the one category of target that has always sat at the center of the deepest human question in scientific history. The universe is enormous beyond any scale that language can honestly convey. There are more stars in the observable universe than grains of sand on every beach on Earth combined. Most of those stars have planets. We now know this. The question was never whether other planets existed. The question was always whether we would ever be capable of actually seeing them, studying them, and eventually understanding them well enough to know whether the conditions for life are rare or common, precious or abundant, an accident unique to our small corner of the galaxy, or the inevitable output of a universe that was always, in some meaningful sense, doing exactly what it appears to be doing here. TWA-7b does not answer that question, but it changes the nature of the search in a way that makes the question feel, for the first time, genuinely answerable. Not by this generation of telescopes alone, but by the trajectory that this generation of telescopes has established. The path is now visible. The first step has been taken in a way it never truly had been before. And somewhere out there, 111 light years away in the constellation Antlia, a young Saturn-sized world continues its slow, cold orbit around a star that is still in the process of becoming itself, completely indifferent to the fact that a species on a pale blue planet in another solar system has, for the first time, looked up and seen it clearly. What comes after that moment? What does the universe reveal when the next instrument is turned on and the contrast ratio improves by another factor of 10? What is sitting in the debris disks of the other young nearby stars that Webb's follow-up campaign is now examining one by one? And what happens to the human understanding of our own place in the cosmos on the day, which is coming, when the image on the screen is not a Saturn mass gas giant in a cold outer orbit, but something smaller, warmer, and disturbingly familiar? Nobody knows. And that uncertainty is not a failure of science. That uncertainty is science working exactly as it is supposed to, because every answer so far has only ever led to a deeper, more beautiful, more urgent version of the same question. And right now, for the first time in history, we have the tools to start getting serious about finding out.